Now let's read this problem together. The Electropoly Corporation is the world's leading manufacturer of slip rings. A slip ring is an electrical coupling device that allows current to pass through a spinning or rotating connection, such as a gun-turret on a ship, aircraft, or tank. So these first two sentences give us some just general information. And then starting from here, the company recently received a $750,000 of order for various quantities of three types of slip rings. And each slip ring requires a certain amount of time to wire and harness. And when you read to here, you should relate this to the Blue Ridge hardtop problem, where manufacturing certain types of models require some resources. Here, the resources will be the time to wire and harness, and those resources usually represent the constraints. Then this following table summarizes the requirement of the three models of slip rings. First row is the number ordered. Okay, that means we need to fulfill those orders. And the second and the third row gives the unit of resources for the wiring hours and the harnessing hours required to manufacture this model 1, 2, and 3. These are the same like the tubing, labor, pumps, resources in the Blue Ridge hardtop problem. Okay. Unfortunately, this company does not have enough wiring and harnessing capacity to fill the order by its due date. They only have 10,000 hours of wiring capacity and 5,000 hours of harnessing capacity to devote to this order. Okay, so again, we see limited resources. So no matter how many Model 1, Model 2, and Model 3 that we are going to produce, we only have those 10,000 and 5,000 hours of harnessing and wiring hours to use. However, this company can subcontract any portion of this order to one of its competitors, and the cost of subcontracting, which is to buy, are given here for each model. And also the cost to make in-house are also given in this model. And this company wants to determine the number of slip rings to make and the number to buy in order to fill the customer order at the least possible cost. Okay, so with this first reading of this problem statement, we can abstract those important information like this. Okay, so they received this order of $750,000. Okay, and this table gives the resources needed, and also resources available. Okay, and they also tell us that they won't be able to fulfill all of these orders by themselves, manufacturing in-house, but they can buy from somewhere else. That's the outsourcing. And the cost to buy and cost to make are given here. Then they want to determine the number of slip rings to make and the number to buy in order to fill the customer order at the least possible cost. This last sentence is pretty important. It gives us two parts of information that's related to our OR model. First, wants to determine. That's the decision. Okay, and what's the decision about? It is to decide how many number of slip rings to make and to buy in order to fill the customer order at least possible cost. And here, at least possible cost. This gives us the objective. Okay, and we want to minimize total cost. And these are our decision. This is our decision. Okay, so now let's define our decision variables. Our decision variables will be how many number to make and to buy. But should we have just two variables or more? Then let's look at this. How many models do we have? We have 3 models of the slip rings. And so we need to decide how many model 1 to make and how many model 2 to make, how many model 3 to make, as well as how many model 1 to buy, model 2 to buy, and model 3 to buy. With that, we know we need 6 decision variables. Okay, and of course we can use x1 through x6 to represent those 6 decision variables. But we can also use some symbol that's easier to represent or more meaningful that represent what we are trying to solve. So here I'm going to use M1, M2, and M3 to represent the number of slip rings in model 1, 2, 3 to make in-house. Okay, and use B1, B2, B3 to represent the number of slip rings in model 1, 2, 3 to buy. So these are our decision variables. And then we'll need to define the objective function. We said that the objective is to minimize the total cost. And here the total cost includes 2 parts. First part will be cost to make, and the second will be cost to buy. Okay, and in this table, what is given are those units cost. And the total cost would be the unit cost times how many to make. For example, for model 1, how many are we making? We don't know, right? But we use the M1 to represent the number to make for model 1. So here, we want to minimize 50 times M1. That is the total cost of making model 1 plus 83 times M2 plus 130 times M3 plus 61 times B1. That's the number to buy. Okay, plus 97 B2 plus 145 B3. So these are the total cost to make versus to buy. Now let's look at the constraints. Okay, so here we've already used this table. So check. Okay, and we'll go back to the problem at the beginning. Do we need to use this $750,000? This is the amount of order received. And since in the objective function we've already minimized the total cost, we don't really need to use this number because it's a fixed order. And as long as we minimize the total cost, then the total profit, which is this 750,000 minus whatever this total cost comes up with, then we will maximize the profit. Okay, so check. We already look at this, and we don't need to use it. Then let's look at this table. These two should be very familiar to you now, in regard to how to write the constraint out based on these. Okay, and here I like you guys to write the constraint yourself first. Okay, so write the constraint for the number of hours of wiring needed to make model 1, 2, 3 should be less than equal to the amount of total wiring hours. Okay, and also the second constraint would be the number of hours used for harnessing to make model 1, 2, and 3 should be less than equal to the 5,000 hours of harnessing available. This is exactly the same format as what we created for the Blue Ridge hot problem. So the resource used or resource needed need to be less than or equal to resource available. So please write these two constraints yourself. Okay, hope you are done. So I'll write this out here. Subject 2x1 plus 1.5x2 plus 3x3 need to be less than equal to 10,000. Then 1x1 plus 2x2 plus x3 need to be less than equal to 5,000. Okay, so the first is the wiring hours. The second one is the harnessing hours. And these two constraints represent resource needed or used need to be less than equal to resources available. Okay, so these are the first group of constraints. Then let's go back to see if we need some other constraints. Okay, so these two rows already used. Check. We used these and also used these ones. Then what we didn't use so far are those numbers. These numbers represent the customer order that we have to fill. Remember, in this last sentence, we said we need to fill this order. Okay, so no matter how many of Model 1 you buy and how many you purchase, altogether, they should fulfill this order of 3,000. Okay, so with this analysis, we know that, okay, the number we buy for Model 1 and the number we make and the number we buy add up together should fill this order. So that means should be equal to this one. Okay, so that gives us our third constraint, which is M1 plus B1 should be equal to 3,000. With the same logic, we can write constraints for the other fulfillment of Model 1, Model 2, and Model 3. So the number you make and the number you buy for Model 2 should be 2,000. Number you make and the number you buy should be equal to 900. Okay, so this is the second group of constraints, means total of lip rings should be equal to order number. Okay, now I've got a question here. For those signs, equal to means that we'll just fulfill the order. And can we change it to greater than equal to sign? Let you think about this. Okay, to answer this question, first let's think about what does greater than equal to sign mean. A greater than equal to sign here means we want to make and buy at least 3,000 Model 1 so that we can fulfill the order. Okay, and we make and buy at least 2,000 of Model 2, and we make and buy at least 900 for Model 3, so the order can be fulfilled. But people would think, is it economical to make and buy more than what is ordered? You think, no, it's not economical, right? So why should we use greater than equal to sign? Okay, and the reason is that, especially when we go to later chapter 6, when we set constraints on those decision variables to be integers, meaning that we don't buy or make a half slip ring. Okay, we always make an integer number of those slip rings. Here we don't impose those constraints because they use a different kind of algorithm to solve, and we'll talk about that later. Even though in this problem it makes perfect sense to impose those integer constraints, but we won't write it here. Okay. Especially when we impose those integer constraints, having equal to signs will be too restrict, and sometimes we may not be able to find a feasible solution. Okay, think about this. Last week we talked about graphical solution, and we talked about some special situations. When you have equations in your constraints, think about what the feasible region becomes. The feasible region becomes a line, right? Because of those equations. So that shrinks the possibility of finding a feasible solution, because you may not be able to find a solution that satisfies all those equations, and it's within the feasible region. So if those constraints are inequalities, that improve our chance of finding a feasible solution. Okay, that means when the optimal solution is found, some of those left-hand side may not be strictly equal to the right-hand side. So this one may be, say, 3,200, and this one may be 2,000, and this one may be, say, 902, in order to find a feasible solution. Okay, and in this problem, if we change it to greater than or equal to, it will still give us exactly the same result. Why? Because we've already got this objective function here, right? Our objective is to minimize the total cost. So as long as all of those constraints are satisfied, even if we change it to greater than or equal to, if we can find a feasible solution at this straight equal to, the solution will be straight equal to. It won't, the left-hand side of those constraints won't go beyond what is required. Okay, because the objective function will force those m1, m2, m3, b1, b2, b3 numbers to be as small as possible to minimize the total cost. Okay, think about this again. We are saying that because of this minimization objective function, which will force these m1, m2, m3, b1, b2, b3 to be as small as possible. So even if we change these signs from equal sign to greater than equal to sign, m1, m2, b1, b2, b3, m3, they will be as small as possible. So if we can find the solution at a strictly equal level, they won't be greater than that. Okay, but changing those signs to be greater than equal to sign improve our chances of getting a feasible solution. Okay, so we'll talk about this in more detail and illustrate with more examples later this semester. Here I'll just mention this for your information. Okay, and in general, we just want to have those constraints as less restrictly as possible to improve our chance of finding feasible solutions. And because of the objective function, they will have the same effect as equal signs. Okay, with that said, let's see, are there any more constraints that are missing? Yeah, the non-negativity constraint, right? So all the m and all the b need to be greater than or equal to 0 for all I goes from 1 to 3. And that's our model. Okay, so this is the model that we created for this problem. So just a brief summary of the model we created. First, we define the decision variables using some meaningful letters to represent the number to make and the number to buy for each model of slip rings. Next, we formulated the objective function using the minimize the total cost of filling the order, and the total cost include two parts, the cost to make and the cost to buy. Then we define the constraints. The defined constraints that are the number of models of the number of slip rings of each model that we make and buy should fulfill the number ordered for each model. And we talk about this equal sign here could be changed to greater than equal to sign, and we should have the same result. And then the resource constraints, which we modeled earlier just now, are the resources needed should be less than equal to resource available. Then we add the non-negativity constraint, which would be all the decision variables should be greater than equal to 0. And that's a complete model.